this lecture, I'm going to talk a little bit about rational exponent notation. We're just going to focus in on the concepts here of rational exponents. And when I say rational exponents, I really mean fractional exponents, or exponents that can be expressed as fractions. Few prerequisites are required here. You have to know what an exponent is, obviously. You have to be very familiar with laws of exponents. In fact, you might as well consider yourself an expert with laws of exponents before coming in and doing this section. You should be very, very familiar with radical notation. However, I'll talk about that a little bit here. And then extremely familiar with integer exponents, negative exponents, and zero exponents. We'll first start this with just a review of what radical notation actually is. I debated on how I was going to write this, and I decided with writing this as an equation. The nth root of a is equal to b implies that b to the nth is equal to a. Now, let me give you an example of what I mean, and then I'll talk about the parts of this. A simple example is that the third root of 27, well, that happens to equal 3. Why? Well, because, actually I shouldn't do those, I'll say because this 3 to the third power is equal to 27. In other words, this 3 raised to that third power is equal to 27. And in fact, we could see this in a lot of cases, like let's do the fourth root of 16. That's equal to 2. The reason why is because 2 raised to the fourth power is equal to 16. Again, 2, and let me go ahead and circle this up, 2 raised to that fourth power is equal to 16. So raised to 2 raised to the fourth power is equal to 16. Now, I want to, the reason why I'm kind of using this circular notation here is because I'm going to use this when we introduce a concept called logarithms in the future. So I just want us to get used to this circular argument that these two notations imply the same thing. They're two equivalent notations. So when somebody says, oh, the third root of 27 is equal to 3, you could say, oh, you mean 3 to the third power is equal to 27? Or if somebody says, oh, the fourth root of 16 is equal to 2, you could say, oh, you mean that 2 to the fourth power is equal to 16. And in fact, we're often used to seeing positive numbers underneath radical signs, but it doesn't have to be that way. You could say the third root of, oh, let's go a negative 8. That's equal to negative 2. The reason why is that negative 2 raised to the third power is equal to a negative 8. Just look at that circular argument here. Negative 2 raised to that third power is equal to negative 8. I'll write the little raised 2 here. I didn't write 2 right there, but I should have. So that's a little review of radical notation that you should be very familiar with at this point. Anyway, a couple definitions here. The n is called the index of the radical, and often we don't like indices of radicals to be anything except for natural numbers. So this is numbers like 1, 2, and so on and so forth. The symbol itself is called the radical symbol, and the interior of that radical function, because that really is a function, I'm plugging something in, I'm getting something out, is called the radicand. Now those are all definitions. I personally don't really care to know all the definitions, just as long as you know how to use them and can talk about them intelligently. That's all that really matters in the real world. However, if you have an instructor that prefers that you know every single little definition, then there you have it. So I decided to write down a few extra examples here because I think it's very important to get some practice. So each of these we're going to go ahead and simplify. And again, following that idea of how to find the root of a number here, we'll go ahead. I often do this. The cube root of 64 is equal to some number I don't know. And then I'll use that circular argument that x raised to that third power should equal to 64. So this is the raised 2. I know it's maybe a little bit small unless you increase the size of this video, but so this implies that we want to find an x so that when we raise it to the third power, it is equal to 64. And we know that x, a number to the third power equals 64. You could try, you start with smaller numbers. Start with 2. 2 to the third power, that's 8. 3 to the third power, that's 27. 4 to the third power, that actually is 64. So this is equal to 4. So the third root of 64 is 4. The reason why? 4 to the third power is 64. Let me just erase that out and sub in 4 so you can see it. 4 to the third power is 64. Now, just to remind you, the answer is 4, not 4 to the third power equals 64. The answer here is 4. What we want to do is simplify the cube root of 64. An easier way to say that is just the number 4. Now, a lot of people can look at this stuff and say, oh, I already know. I immediately know the cube root is 64. So if you know that, don't go through this process. Just write down the number. I'm just showing you kind of an interesting way to think of how to find the root of a number. And the reason why I'm doing this, and I will continue to do this, is because it is a great parallel to a future topic in logarithms. So the fourth root is 625. I don't know what that is. I'll call that x. And of course, that means that if I wrap that x up and say x to the fourth power is equal to 625, then let me go ahead and rewrite that and say, great, I'm looking for an x that when I raise it to the fourth power is equal to 625. Again, start with small numbers because it's really difficult for you to take numbers like 57 and raise it to the fourth power. You just can't, not in your head, you're just not going to do that. So start with small powers like 2 to the fourth power. Well, that's too small. 3 to the fourth power, that's 3 times 3, which is 9, times another 3 times 3, which is another 9, so that's 81. That's not going to work out. Then you move on to 4, and you'll find out quickly that that doesn't work out. But 5 actually will work out. 5 times 5 is 25, and another 5 times 5 is another 25. 25 times 25 is 625. So the answer here is going to be 5, and the reason why is because 5 raised to the fourth power is actually 625. So our answer is 5. Let's move on to the next one here. We're looking for a number such that when we raise it to the fifth power here, it will equal 100,000. Now, the clue to what this number is going to be is the fact that we're looking to raise a number to the fifth power to become 100,000, and that's a power of 10 right there. In fact, I'm going to guess that it's going to be 10. I'm thinking that the fifth root of 100,000 is going to be 10. Let's check it out. 10 to the fifth power is 1 with 5 zeros after it, and 1 with 5 zeros after it is 100,000, which is 100,000. So that does work out. And now we move on to this next example. This next example, when I see something with a little bit of math inside of it, so here's a function. Again, radicals are functions. But this function has a fraction inside of it. A function with a fraction. And the first thing I want to do is simplify that fraction if it can be simplified. So I'll see if there's any common factors between the numerator and the denominator, which there are not. So it's just a little check I do. And then I ask myself, well, I know this is going to equal something. I just don't know what that something is, so I'll call that x. And I'll ask myself, what do I raise to the third power to become a negative 8 over 125? So what do I raise to the third power to become a negative 8 over a 125? First thing I'm going to notice here is that any number that I raise to a power, if I want that answer to be negative, that number inside that x should be negative. So I'm going to write a little negative sign out front, and I'm going to double check that. If x were negative, I'd have negative times negative times negative, which would definitely give me that negative right there. So we're okay. And now I need the numerator to become 8. What number do I raise to the third power to become 8? Well, that would be 2. And I need the denominator to become 125. What number do I raise to the third power to become 125? That'd be 5. So therefore, it must be true that the cubed root of a negative 8 over 125 is equal to a negative 2/5. The reason why? Because a negative 2/5 raised to the third power is equal to a negative 8 over 125. So I'm just using that circular argument the entire time. This next example, example E here, again, I have no idea what it is, so I'll write X in here. And I'll say, what do I raise, what number do I raise to the fourth power to equal a negative 16 over 81? So what number do I raise to the fourth power to equal a negative 16 over 81? And you might notice immediately that there's no such number, because when you start taking even powers of numbers, if your number would have started as a negative number in here, if x were negative, well, when you square it, it becomes positive. When you cube it, it becomes negative again. And when you raise it to the fourth power, it has to become positive again. So there's no possible number, no such number. No way that we can get a number such that when I raise to the fourth power, it becomes negative. So this answer, some people will say no such number, some people will say it doesn't exist. It's actually not a real number. Technically, there is a number that makes this true, but it's just not a real number. And for right now, let's just deal with real number answers. Something I didn't say in that last example, but I will say it now in this example F, this final example here, is that, again, when I have a function and the inside of the function has a little math going on, I'll likely want to simplify it if I can. It might make my life a little bit easier. So in this case, I see that I have a fraction that actually will simplify because both numerator and denominator are divisible by 2. If I divide 2 out of both numerator and denominator, I'll get 16 over 81. And now I know that won't simplify any further, so I want to just find a value of x such that when I raise x to the fourth power, I will get 16/81. So let's see what that is. X to the fourth power, I want that to turn into 16/81. And notice that this is almost the same question as before, but this time I'm actually asking, when is x to the fourth power equal to a positive 16 over 81? Well, I happen to know that for the numerator, a number to the fourth power that becomes 16 is 2. 2 to the fourth power will be 16. And actually, I should draw that in green here. And a number to the fourth power that equals 81 is actually 3. So turns out the fourth root of 32 over 162 is 2/3. And again, the reason why is because, well, 2/3 to the fourth power is equal to 16 over 81. So to get into the idea of what this section, or this lecture, I guess, is really focused on, is since we're dealing with the concept of rational exponent notation, I'm not really going to do a lot of examples here, but I want to introduce the idea of it. B to the 1 over n, so that's the exponent on that is 1 over n, is defined to be the nth root of b, where n is a natural number. Now remember, this notation here means an element of, and then that n with a bar on it is the set of natural numbers. So I'll write that in here. So for example, 4 to the 1/2 power is defined to be the second root of 4. And we happen to know what that is, by the way. The square root of 4 is just 2. Let's see, 27 raised to the 1/3 power is just defined to be the third root of 27. And we happen to know the third root of 27 is 3. and so on and so forth. So you could deal with larger powers and negative numbers even. So -8 to the 1/3 power is the third root of a -8, which will be a -2. Now, this notation, a lot of people have a hard time and want to know why we've introduced this new notation. The new notation actually is a more powerful notation. Radical notation only works for a while in mathematics and then starts to fall apart. So, I mean, it doesn't really fall apart. You could use it. It just gets bulky to use. So I highly recommend that you start thinking of rational exponent notation more than radical notation. So whenever you see somebody write something like, oh, I need to find the cubed root of some number x, you could say, oh, you mean you need to find x to the 1/3? Yeah, that type of thing. It's very important because eventually you get to like the 7th root of some number. And that's just so bulky to write. A lot of people don't understand what a 7th root is. A lot of citizens don't realize that you can even have a 7th root of a number. So it's much easier to say, well, let's just write number raised to the 1/7 power. Because that, for some reason, a little bit easier to work with, to be very honest with you. So that's how rational exponent notation works. Now that I've kind of given you this idea of what a rational exponent is and how the notation works, we're going to, in the next lecture, use it in examples. But before we do, I'm going to introduce just one more little rational exponent notation definition. Not really a definition, more of a theorem. And I've decided to write this out as I talk about it. So every once in a while, you get a radical that's like the nth root of a number, let's say. And the number that you're taking the nth root of is a powered number. So in other words, it's like b to the nth power. Well, we can write this using rational exponents, and it's actually it looks better than this, to be honest with you. So let's see how that would look with rational exponents. First of all, we know from the last slide or the last page that this is going to be b to the nth power raised to the 1 over n power, right? Because the nth root just means the 1 over nth power. But now notice that this is b to a power raised to a power. And we know that we have that old theorem, let me write it over here, that b to the m raised to the p power is equal to b to the m times p. So this must be b to the m times 1 over n, or in other words, b to the m over n. And what's great about this notation is that I see immediately in it that the n is the root that we were taking, the nth root, and the m, the numerator, is the power. So we were taking the nth root of b and raising that to the mth power. Well, technically, we're taking b and raising it to the nth power and then taking the nth root of it. But what I just said is not incorrect, because what if somebody came along and said instead, you know what, I don't want you to raise b to the nth power and then take the nth root. I would prefer that you take the nth root first of b and then raise that answer to the nth power. The question is, are these two statements different? And the easiest way to answer that is to use rational exponent notation. First of all, inside this parenthesis, that's just b to the 1 over nth power. The exterior of that parenthesis is still the nth power. And remember, powers to powers, they multiply, so that's just going to equal b to the 1 over n times m. And again, that'll be b to the m over n. And look, these are the same notations and still the same meaning, in fact. That n was the root, so the denominator is the root, and the numerator is the power. We are going to use this idea over and over and over again for the rest of the lectures involving radicals, because personally I do not like radical notation. I like to change things to rational exponent notation. It's just a much better notation. So my advice to you, doesn't matter if you're in my class or you're in somebody else's class, my advice to you is the following. When you see a problem that involves a radical, I would immediately change that to rational exponents from this point forward to get yourself practiced with the notation so that you know the square root of a number is just the 1/2 power of a number. Trust me, that will pay off dividends to you in the future.